Hi everyone, my name is Avijit Gupta and I'm the Senior Product Manager on Azure Cosmos DB for PostgreSQL team. In the session today, we are going to talk about building efficient data architecture for multi-tenant SaaS apps on Azure Cosmos DB for PostgreSQL. We'll be starting with looking at some key feature implementations and then try to understand them through demo. So let's get started. So this is an excerpt from Wikipedia where multi-tenancy is defined as a software architecture where a pool of resources are used to serve multiple tenants. Here, a tenant is a group of users differentiated through the privileges over the resources. At a high level, multi-tenancy involves three broader types of implementations with two key objectives. Objective one is building for isolation. This requires a physically isolated environment per tenant. And this can be achieved through separating tenant per database or tenant per schema model. The pattern is more commonly adopted in healthcare or banking industry. Objective 2 is building for scale. This requires utilizing common table to host data for all the tenants. Benefit with this approach is it avoids a lot of operational overhead of individually handling every tenant. Core influencing reason to go with either of these options involves compliance requirement of different tenants, number of tenants on the platform, performance SLAs that we guarantee on our platform, and the customization that we want to permit on our platform. So let me introduce Azure Cosmos DB for PostgreSQL, which is a natural fit for a multi-tenant use case. It is a distributed database with some core feature addressing major issues raised by our multi-tenant customers. Issue number one is performance bottleneck. As the data size grows per tenant, we observe the data or index doesn't fit into the memory, which leads to decline in the performance of our queries. Azure Cosmos DB for PostgreSQL provides the inbuilt option of sharding the data, which allows preserving indexes in memory, and additionally, it co-locates the related data for individual tenants. Issue number two is scalability. As the customer onboard more and more tenants to the platform, their natural worry is if a single node relational database would be able to serve for the required scale. Azure Cosmos DB for Postgres natively support for scale-out functionality with absolutely no downtime. And it also enables in isolating the tenant if the need arises. Issue number three is tenant management. As we hit the issue of performance and scaling, the need arises for moving the tenant to a new node and write an application logic for routing the queries. Effectively, this is reinventing the wheel of sharding. Azure Cosmos DB for Postgres provides support for auto sharding, and it takes care of the routing the queries. Additionally, we also get to observe the query patterns per tenant through the inbuilt monitoring views. So let us observe the key features that we talked about with the simplified example schema. So here is a simplified B2B electronic e-commerce store. We are registering different stores as tenants in the tenants table and their corresponding chain of inventory in the products table, while all the sales on the platform will be captured in our orders table. The important thing here is that we are sharding all these three tables on a common key. So let us understand more around the impact on data placement due to the choice of a common key. On the current slide, upper half represents the view to the application, while lower half represents the internal persistence of the tenant's data. In the current example, we have two worker nodes existing in the cluster, and each of these nodes contain two tenants. Important thing to observe here is that we are keeping the related tenant data across the tables persisted together on a same node, which helps in avoiding cross-node queries and brings efficiency in terms of utilization of resources as well as in terms of performance. So let us understand this through a demo. So for the demo purpose, we have already created these three tables, tenant, product, and orders table on the database, and we have populated some data taken from Kaggle. Let us first review the cluster. So we can see there is one coordinator existing in this cluster with two worker nodes. and should have shard flag tells us that the actual tenant's data will lie on these two worker nodes. Let us verify if there is any table that is already distributed. Currently, we do not see any table distributed on the database. Azure Cosmos DB for PostgreSQL provides the inbuilt function of sharding the dataset. The function takes four parameters: table name, sharding key, shard count, and collocate with. Shard count and collocate with are the optional parameters, wherein shard count has a default value of 32, and collocate with is required only when we are explicitly willing to collocate the data of current table with an already existing table. So let's try to distribute these three tables. So the distribution is completed. Let's run this query again. Now we can see that orders, products, and tenant table all have been distributed, and they are distributed on a common key. And they have equal number of shard count with a collocation ID. Collocation ID effectively could be different for another set of tables from the structure, which are meant to serve a different purpose on the platform. Since we have already distributed this data set, let us now review how does the data placement look like. In this case, we are looking for data for tenant 3, and we can observe that tenant, product, and orders, all these three tables are actually co-located on a single worker node, which is worker node 1. Let us see this again for another tenant. So for tenant 2, we can see the actual data for all these three tables are located on worker node 0. So till now, we were able to shard the data using inbuilt function, and the system is smart enough to distribute this newly created shards evenly, and it also collocates this data for efficiency reasons. Now let us review some common query patterns for multi-tenant SaaS apps and understand how does the data placement help us with achieving this efficiency. So the scenario one is where we are typically doing an update or delete of a data from an existing data set. So in this example, we are doing an update of orders table for a quantity attribute where order ID is there is an order ID value we have picked. Let's try to look at the execution plan. We can see that we have three tasks generated. In the previous step, we actually created three shards for the orders table. And now we see there are three tasks generated for by running this query. In the execution plan, we can see that we are hitting worker node 1, worker node 0. There are two shards located on worker node 0, and there is one shard located on worker node 1. And we can see that we are hitting all these three shards. Effectively, when we look at the rows being hit under these shards, we see 0 records being touched on those nodes. While there is one row touched on worker node 0, which is wherein we see that the shard that actually holds the data is orders 102052, while the other one also doesn't have any data modified. Now let us try to add a filter on tenant ID and re-review this execution plan. After running the same query again with the tenant ID filter, we observe that there is just one task created which hits the actual shard which contains the real data. So effectively, we are scoping the query to just access the shard which actually contains the data instead of parallelly accessing all the shards that exist for the table. Now let us look at another example where we are going to run through a join and a group by query together. In the example, we are trying to get sales of different products for a given tenant in a given month. So in this example, we see that we are looking at June month's data for tenant 1 and trying to pick the product for which we want to see the number of orders placed during the month, average units sold per order, and then we want to also look at the total revenue generated with the sale. On running this query, we can actually see that there is just one task created, and this task actually hits just one worker node 0. Effectively, we can see in the execution plan that there is orders 102050 and there is products table 102047. Both of these tables are co-located on single node and effectively doesn't require us to do a cross-node query. So effectively, we are able to get the output from running a query on a single node. So we can see that by sharding the data, we are querying a smaller data set. And further, by scoping the queries for different query patterns, we could add efficiency with the utilization of available resources. So let us get back to our PPT. So this is our second feature, which is tenant isolation. The left pane here shows the before state of our data placement, and the right half shows the data placement post doing the tenant isolation. In the current scenario, we have two worker nodes, two tenants each, and we are trying to isolate tenant ID 4, which is effectively the store 4 data to a new node. This will be achieved in 3 steps. Number 1 will be adding a new worker node to the cluster. And then step 2 will be shard 3 contains data for two different stores, which is tenant ID 2 and tenant ID 4. So effectively, we need to isolate tenant ID 4 to its own shard. So step 2 will involve isolating the tenant 4 to its own shard. And then step 3 will actually move the data for the newly created shard from worker node 2 to the newly created worker node 3. Let us review this through our demo. So now as part of demo 2, we have already triggered the scale out step. And now we can actually see a new node added to the cluster. We can see private W2 is the new node available on this cluster. Now let us look at the data for tenant 4 and tenant 1. So by running this query, I can see that tenant table for tenant ID 1 and tenant ID 4 is actually located together into the same shard, tenant underscore 102044, and it is located on private W0 node, which is our worker node 0. So step 1 will involve isolating the tenant to a new shard. So let's run this query and see, and let's run this query and move tenant 4 into its own shard. Post executing the isolation of tenant function, we are able to see a new shard created for tenant ID 4. Now let's review the tenant ID and the shard ID key value. We need to key in the shard ID value here and provide the source server name where it is located, where currently it is located, provide the port number, and then provide the destination server where we want to post this shard to, and then the destination port number. So let us run them step by step. So one of them has moved to a new node. Let's run the other two as well. Let us now review the current location for tenant ID 4. We can now see that tenant ID 4 has been moved to a new node added to the cluster, which is worker node 2. So to summarize, as we discussed in the previous slide as well, there were 3 steps involved with tenant isolation. Number 1 was adding a new node to the cluster. Number 2 was isolating the tenant to its own shard. And number 3 is moving the shard from the source node to a destination node. So this completes our demo 2. So let us take a look at demo 3. So as part of demo 3, we want to look at the system available views that Azure Cosmos DB for PostgreSQL provides, and how does it provide some information about the query patterns. So here I have executed the query against cytostat statements, and we can see the different kind of queries being executed for different tenants and how many number of execution has happened for each of these tenants. We are still working on improvising and adding more features to this. But this is the current state of information that is currently available on the platform. So let us summarize what we discussed in our current session. We learned about capabilities offered by Azure Cosmos DB for PostgreSQL in the current session. We looked at data sharding and how it helps in co-locating the data, which further helps in improvising the performance. We also looked at some of the SaaS query patterns and learned scoping of queries for multi-tenant use cases, which allowed us to use the cluster resources more smartly and efficiently. We also experienced scaling out the cluster and then performed tenant isolation to the newly added node. Effectively, both of the scale out operation and tenant isolation were completely online operations and will not affect writes or reads to be affected. And finally, we looked at the internal view, internal monitoring view, which gives some insight about the queries being triggered against different queries being triggered by different tenants. So scan this QR code or refer to this link for learning more about hosting multi-tenant applications on Azure Cosmos DB for PostgreSQL. Happy learning.